Design and development of an ultra-sensitive, label-free, non-invasive nanobiosensor stands for breast cancer risk assessment in rural women exposed to biomass fumes. A project conceptualized and implemented by Division of Environmental Biotechnology, Genetics and Molecular Biology, Indian Council of Medical Research, National Institute for Research in Environmental Health, Bhopal. Objectives achieved: to synthesize ultrasensitive, label-free, semiconductor nanocrystals-based biosensor for detection of circulating cell-free miRNAs. To evaluate the performance ability, specificity, and sensitivity of the developed nanobiosensor using a selected panel of cell-free circulating nucleic acids aberrantly regulated in rural women residing for more than 10 years in the high indoor air pollution zones, exposed to biomass fumes. To validate the performance of the nanobiosensor through testing the specificity and sensitivity in control settings. Background of the study. Around 2.4 billion people worldwide use solid biomass fuels for cooking, causing air pollution and illness. Long-term use may lead to epigenetic reprogramming, including increased breast cancer risk. This study, conducted in rural areas of India where unclean cooking fuels like wood, charcoal, and cow dung cakes are prevalent, set out to analyze the molecular processes triggered by biomass fumes. We also designed a triple nano biosensor for simultaneous evaluation of the effects, aiming to determine their potential as early risk assessment. And breast cancer care indicators. First, we collected 366 blood samples from rural areas of 6 districts: Batol, Chhindwara, Dhar, Gwalior, Morena, and Sagar of Madhya Pradesh, which were then separated into plasma and lymphocytes using density gradient centrifugation. After the blood collection and isolation, we performed expression profiling of miRNAs, mRNAs, and LNCRNAs. The miRNA expression analysis was performed through real-time qPCR using the SET laboratory protocol. The screening of miRNA sequences was done by using the MIR-base and DynaMIR PathWeb databases. For mRNA and LNCRNA expression analysis, we used a PCR-based method. The isolated RNAs were subjected to cDNA synthesis, followed by real-time PCR. After completion of the programmed PCR cycles, CT values were obtained and represented as mean CT values. The amplicons were then loaded and run on the 2 to 3% agarose gel at 85 volts for 45 minutes. The gel images were captured in UV Biorad GelDoc XR Plus using ImageLab software. Upon deregulation, these entities trigger initiation and progression of different type of breast cancers like invasive ductal carcinoma, inflammatory breast cancer, or invasive lobular carcinoma. In the expression analysis of 366 collected sample, we found that microRNA miR34A, LNC RNA, NRIL, and messenger RNA PTEN play a crucial role in the initiation and progression of biomass fumes-associated breast cancer. After identification of the triad, we moved on to the development of the triple nano biosensor. A complex process involving 3 different semiconductor nanocrystal. These quantum dots were activated and attached with a protein called streptavidin using carbodiamide chemistry. Carboxyl groups on QDs were coupled with amine groups of biomolecules for nanoconjugates. Dilute QDs were pre-activated with EDC and NHS solutions, incubated, and then streptavidin added. Free QDs were separated and conjugated QDs stored at 4 degrees Celsius for further use. Fabrication of captured component of the nanobiosensor is evaluated by fluorimetry analysis. After this, we prepared biotinylated oligonucleotide probes. In this process, the probes were attached to a biotin molecule at 3' position and incubated at a high temperature. Next, the streptavidin-tethered quantum dots were conjugated with biotinylated oligonucleotide probes, resulting in the fabrication of the triple nanohybrid. The evaluation of these newly developed nanohybrids is the most important step, ensuring their efficacy, safety, and reproducibility. We have performed a comprehensive evaluation of the developed nanohybrid's binding capabilities, quantification of its performance parameters, and exploration of its stability in various biological samples. The triple nanohybrid applicability was assessed through comparative analysis of fluorescence responses from capture and detector hybrids fabricated using a standard protocol for detecting target 34A, ANRIL, and PTN-enriched samples and triplicates. We also perform sensitivity analysis of developed nanohybrid. The prepared conjugates were tested for their specificity to precisely identify the target 34A, ANRIL, and PTN in a pool of different mixed miRNAs, LNCRNAs, and mRNAs species amplicons. For the specificity investigation, different miRNAs, LNCRNAs, and mRNAs amplicons were pooled together and mixed with nanohybrid. A method for quantifying and visualizing. The developed a nanohybrid triad would never have been completed without conducting high-resolution fluorescence colocalization studies. This allowed us to understand how the nanohybrids would interact with respective target molecules. The publications generated during this. Our findings have been published in highly reputed international journal, Drug Discovery Today, with impact factor 8.36. Case studies in chemical and environmental engineering with impact factor 7.93. ACS Omega with impact factor 4.1. Journal of Pharmaceutical and Biomedical Analysis with impact factor 3.4. We also protected our developed technology by filing a patent. A method for identification of RNA methylation in biological samples. A new point-of-care tool called Nidain was developed as a nanoimmunode assay to rapidly identify the triad related to air pollution-linked breast cancer. Thank you so much.